Hi students, welcome to HSC Chemistry and Module 5, Equilibrium and Acid Reactions. This is video number 17 and we're going to just review and extend our understanding of dissolution of ionic compounds. So we've already looked at the fact that an equilibrium can actually be set up by substances, ionic substances, which dissolve in water. We've looked at the fact that in any ionic crystal, in a crystal array, you have alternating cations and anions which are equally distributed around one another in direct proportion to the simplest ratio between those two ions. So in this case, we've got a KCl ionic lattice, and the potassium chloride is dissolving in water, and you can see the little water molecules surrounding each of these. This model kind of describes a little bit about what's happening. So you can see the way that the polar water molecule is oriented is in such a way as to attract the individual ions. So where the ion is a cation or a positive ion, such as it is here, you can see that this is the slightly negative end of the water molecules that are attracted to the cation. Alternatively, you can also see that the slightly positive end of the water molecules are attracted to the anion. So this is how a crystal of an ionic substance is actually pulled apart by water molecules. Water's effect as a solvent is a result of its polarity. So we know that the water molecule is a bent molecule, and there is a polarity created by a slightly negative charge due to the high electronegativity of the oxygen in comparison with the hydrogens, and therefore a slight positivity in the region of where the hydrogens are. This polarity is what is doing all the attracting. So the fact that the water molecule has a positive and a negative side means that, and the fact that it's in liquid means that the molecules can rotate, means they can orient themselves in such a way as to attract those individual ions. Now, one thing that's important to remember is that as the solid is dissolving, or the ions are separating out, dissociating from one another into the solution is becoming more and more saturated. So its concentration will be increasing. And that's because the reaction of KCl solid is initially going to K plus ions in aqueous solution and Cl minus ions in aqueous solution. Now that continues to happen until the solution reaches saturation, and once we reach the point where no more of those ions are going to dissolve, then we end up with a reverse reaction occurring at the same rate as the forward reaction, and this is our definition of equilibrium. So at this stage, some of the ions that are in the solution, such as this one over here, maybe a yellow, this one over here, and this one over here, may subsequently rejoin to become part of the lattice here. And whilst at the same rate, ions that are part of the lattice are also being pulled away from the lattice by other water molecules. So we have this continual movement between ions in the solution precipitating out and ions within the crystal lattice dissolving or dissociating into the solution. Because this is an equilibrium, we can evaluate it in the same way as we've evaluated other equilibria, and that is in terms of how we can change the equilibrium. So the first thing that we can always do is change the temperature. We know that an increase in temperature is going to favour the endothermic reaction, and that's the one that has the positive delta H value. And likewise, a drop in temperature is going to favour the exothermic or negative delta H value. There's another thing that we need to look at here, and we'll look at this in a little more detail later on. What would happen if I was to add sodium bromide to this solution? Well, the short answer is nothing. Because when the sodium and the bromine dissociate into the solution, neither of these two ions are part of the original equilibrium. So as much of those will dissolve and there won't be any interaction. But if instead I was to add sodium chloride, what we have here when this one dissociates is sodium ions and chloride ions. And the chloride ions here are common. So this is what we call a common ion effect. When we add another source of the same ions, we do make a change in the equilibrium. For our purposes, at this stage, before we put some numbers on any of these, we should be able to conclude in a fairly obvious manner that if we were to add a source of additional chlorine ions, then the concentration of the chlorine ions is going to increase, and according to Le Chatelier's principle, the whole equilibrium should shift to the left. This is fine, but we need to know how the equilibrium constant may change as a result of this, and we have a special type of equilibrium constant that we use for dealing with ions in solution, which we will look at in subsequent videos. Thanks for watching.